Hi friends, I am Dr. Prakash bhadane. I am going to deliver the lecture on Fraunhofer single slit diffraction method. In last lecture, we had discussed the concept about the diffraction and types of diffraction. In that lecture, we have also learned three methods of diffraction under the category of Fraunhofer diffraction. First is single slit Fraunhofer diffraction, second is double slit Fraunhofer diffraction, and third one is n number of slit diffraction. Today we will discuss only Fraunhofer single slit diffraction method or single slit diffraction pattern. The experimental arrangement of Fraunhofer single slit diffraction pattern as shown in this diagram. For performing the complete experiment, we must require some specific apparatus. So, there is a requirement of 4 basic apparatus. First is the source, that is monochromatic source. Example is sodium source whose wavelength is 5890 and 5893 Angstrom unit. Second is the screen. Third is the slit which is a AB, and fourth is 2 lenses L1 and L2 lens. The working of Fraunhofer single slit diffraction we can describe by using this diagram. The source is monochromatic source which emits the wavelets or the wave of lights that passing through the L1, and L1 converts this spherical wavefront form of waves into the plane wavefront form. This plane wavefront form of waves simultaneously incident over the slit AB whose width is A. Now, if the size of AB is comparable with the wavelength of incident waves, then there is the process of diffraction, process of scattering. So, after this comparison, the rays undergoes into the 2 path. First, along this direction, that is called as a diffracted rays, means the rays diffracted by at an angle theta. Here we have already shown here theta, and some rays do not diffract and they are propagating along the straight line. So, that rays are called as the undiffracted rays. We can collect these diffracted and undiffracted rays by using the line Cl2. The undiffracted rays are concentrated at the point O and diffracted rays are concentrated at point P. The undiffracted rays forms the point O. That point of O is called as the central maxima because all the wave propagating along the straight line. At the point P, P is the maxima, but the nature of at the point P, P is the minima, and the nature of minima is depends upon the path difference, that depends upon the phase difference in between the diffracted ray. In this system, we would calculate different conditions, the conditions for central maxima, the condition for minima, and the central condition for secondary maximas. In last lecture, we have also distinguished in between interference and diffraction. So, everybody is familiar with the concept of the diffraction. In the diffraction phenomenon, O point is a central maximum point because the intensities are very high, and after the O point all the maximas are called as the secondary maximas because the intensity decreases from O point to the either side of the maximas. So, the nature of intensity is in a decreasing manner, and that is depends upon the value of phase difference and value of path difference. Means the nature of intensity I or the value of I is depends on the value of R, because intensity and R is directly proportional to each other. R means amplitude, means we can say I is directly proportional to the amplitude square. But the amplitude or amplitude of any system, if the amplitude is resultant amplitude, then the value of resultant amplitude is depends upon the value of theta, and theta is the phase in between the rays, and the value of theta is depends upon the value of path, that is path difference. Means if the value of path difference is in a changing form, then it will create the effect over the theta. Due to the change in a del, theta will vary. If theta will vary, means r will be changing form. If r is in the form of different values in a changed form, then the I would be different. Means if we know the delta, then we can calculate the value of theta, then we can calculate the value of r, and at the end we can calculate the value of I. And if we know the value of I, then we can calculate the condition for central maxima, the condition for minima, and the condition for secondary maximas. So our aim is to calculate the value of this intensity and the value of amplitude. If we know this value, then we can calculate these three conditions. So let us find the value of I from r from theta and theta from del. Means first we must find the value of theta. So let us calculate the value of del from the diagram. See, in this diagram, A is the starting point and B is the end point of the scattered rays, because A is edge, starting edge, and B is the ending edge of the slit. Therefore, we can say here this is the starting diffracted rays and this is the end diffracted rays. So let us find the value for this path difference in between starting and end diffracted rays. So for that purpose, we have drawn here AM normal over the BD ray. Means AC is the first ray and BD is the last ray. The resultant path difference in between all the rays we can calculate by drawing the normal from AC to BD in the form of AM. So here in this case, the path difference in between the first and last ray is BM. From the diagram, we can use the property of sine. We can write sine theta is equal to this front side upon hypotenuse. So BM upon AB. Now by rearranging this equation, we can write BM is equal to AB sine theta, but AB from the diagram, AB is equal to E, so E sine theta. So BM is equal to E sine theta, equation number 1. What does mean by BM? BM is the path difference in between first ray AC and last ray BD. So we can write del is equal to E sine theta, equation number 2. If del is E sine theta, then we can calculate the value of phase difference, resultant phase difference between first and last ray. So that is according to the standard equation of phase, which is phi is equal to 2 pi by lambda into del. But del from the equation, which is E sine theta, then this equation becomes 2 pi by lambda into E sine theta. So this is the resultant phase. So from this complete description, we got two relation. First relation for path difference, which is del is equal to E sine theta, equation number 1, and second equation is equation for phase, which is a phi is equal to 2 pi by lambda E sine theta, equation number 2. But our aim to find the resultant amplitude at the point P, or resultant amplitude for this diffraction pattern. So phi is equal to 2 pi by lambda, this is the resultant phase, del is the resultant path difference in between them. For finding the value of resultant amplitude, we will here consider the AB, complete AB divides into the small particles in a small parts. If the plane wavefront incident over the AB at a one time, then each and every point of this plane wavefront act as the secondary source of light, because everybody knows the principle of Huygens. Huygens principle state that each and every point of the wavefront act as the secondary source of light, means AB is act as a plane wavefront, therefore each and every point on the AB act as a secondary source of light. If each and every point act as a secondary source of light, means in between them there is a very small difference, and that difference is a very small. Let us assume that difference is A. A is the difference between or the separation between two waves, means indirectly A is called as the amplitude for the first wave, amplitude for the second wave, amplitude for the n number of waves, because AB divides into the n number of parts. If AB divides into the n number of parts, means there is a number of A is the amplitude for single slit, means the amplitude for n number of slit, n number of waves is also A. Second, there will be the particular part difference in between them, in between first ray and second ray. The separation is a very small, infinitesimally small, that is A in between them, and the part difference between these two successive rays is equal to D. Suppose that D is again very small. Here phi is the resultant part, phase difference, and D is a resultant, D is a phase difference in between the two successive waves. If D is a difference between two successive rays, then we can write here D is equal to, there are n number of particles because AB divides into the n number of parts, therefore we can write here phi divides with n number of parts. Therefore this is equal to 2 pi by lambda into E sin theta upon n, equation number 3. So equation number 3 tell us the value of phase difference in between two successive rays if the complete slit divided into the n number of parts, and the value of amplitude for each wave after dividing the complete AB in n number of parts is A. So A is the amplitude. Now next, if A is the amplitude for first ray, A is amplitude for second ray, A is amplitude for third ray, so A is applicable similarly for all the n number of rays, means the value of magnitude of amplitude is same for all the rays, A1, A2, A3, A4 is equal to A5 up to dash AN. But the equation 3 tell us they are not in the same direction, because in between first and second ray having the phase is D, between second and third is also D, between third and fourth is also D, between fourth and fifth also D, means they are not in the same direction. So in terms of magnitude we can write this equation, but in terms of vector form of amplitude, A1 vector is not equal to A2 vector, A2 vector is not equal to A3 vector, A3 vector is not equal to A4 vector up to last one. So that is not equal to AN vector. In magnitude wise, A1, A2, A3 up to AN are equal, but in vector form, in direction wise, they are not equal. The magnitude are equal, but vector form of A is not equal. So we can't add all these vector directly, and we can't take the resultant amplitude, because these two equation number 4 and equation number 5 are completely contrast to each other. A is magnitude wise equal, but in terms of direction they are not equal. So we can't take the average of all these A, we can't take the summation of all these ray for finding the resultant amplitude. So if we want the value of amplitude, then we can apply the concept of phasor diagram. So I can wipe it for drawing this. So according to the vector diagram, we know that We can draw here the diagram for this n number of amplitudes like this way. Up to the last one. D, 2D, 3D, 4D, last one to the particular value. This is the theta, which is the resultant angle. See, by using the phasor diagram, we can draw here the phasor diagram for n number of vectors. So, A1 vector is here, which having the straight direction, A2 vector having the difference, which is D, A3 vector with respect to A1 is 2D, A4 vector with respect to A1 3D, A5 vector with respect to A1 4D, and up to last one, which is particular value, that is n minus 1D. So, this is the value of A from the diagram. In this diagram, all the vectors are in a addition form, and OA is closing side. That is why OA is called as a resultant amplitude for all these amplitudes. So, our task, our aim is to calculate this OA, which is resultant amplitude. So, for that purpose, we will use here resolving of component method, and according to the resolving of component method, we can write two components for OA. One is along component and second is perpendicular component. So, for OA, the along component we can write R cos theta is equal to A1 cos of, for first A1 which is 0, plus A2 A1 cos of D plus A1 cos of 2D plus dash 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 plus A1 cos of n minus 1D. We know that cos of 0 is equal to 1, therefore, this equation is A1 plus A1 cos of D plus A1 cos of 2D plus A1 cos of 3D plus dash 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 plus A1 cos of n minus 1D. In this equation, A is common, so we can take outside the bracket A. So, A1 inside the bracket 1 plus cos of D plus cos of 2D plus cos of 3D plus dash 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 plus cos of n minus 1D, bracket close. This is the equation number 4. R cos theta is along component of OA. Now, similarly, we can write normal component to OA, and normal component is R sin theta. By using the same method, we can write A1 sin theta, that is equal to 0, sin 0 is 0. So, we can directly write that equation A1 outside the bracket, inside the bracket sin of D plus sin of 2D plus sin of 3D plus dash 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 plus sin of n minus 1D, bracket close, equation number 5. So, here two equations, we got two equations from the diagram. First equation is equation number 4, which is called as along component of resultant vector R, and R sin theta is perpendicular component, normal component to the vector R. We will use first equation for deriving the equation of R. So, we can use the first equation. So, let us wipe equation number 5. We will use this equation after the calculation of equation number 4. So, I am wiping this also. R cos theta is equal to Now multiplying on both sides of this equation with 2 sin theta, 2 sin d by 2, not theta, 2 sin d by 2, then this equation becomes 2 cos theta into sin d by 2 is equal to, दोनों साइड में हमने 2 sin d by 2 से मल्टीप्लाई किया, then this equation becomes a1 outside the bracket, inside the bracket 2 sin d by 2 plus, let us put this, plus 2 cos d into sin d by 2 plus 2 cos 2d into sin d by 2 plus 2 cos 3d plus into sin d by 2 plus dash 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 plus 2 cos n minus 1d into sin d by 2. Observe this equation. In this equation, this part is like 2 cos of A into sin B, and we know that this property 2 cos of A into sin B is equal to sin A plus B minus sin A minus B. So by using this property, we can write this equation, equation number 7 in this form: a1 inside the bracket 2 sin d theta as it is 2 sin d by 2 plus in the second bracket cos d plus d by 2, which is sin 3 d by 2 minus sin d by 2 bracket close plus sin 5 by 5 d by 2 minus sin 3 d by 2 plus sin 7 d by 2 minus sin 5 d by 2 plus dash 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 plus inside the bracket sin n minus 1 or n minus half d minus sin n minus 3 by 2 d bracket close. Equation number 8. Observe this equation, we can solve it by a simple method. 2 sin d by 2 minus sin d by 2 is there. So there is a addition term, इसमें एडिशन करना है, ब्रैकेट अगर हमने निकाला तो लास्ट में हमें मिलेगा a1 inside the bracket 2 sin d by 2 minus sin d by 2, that is sin d by 2. Next plus, because plus sign is there. Observe, this is the first term of this bracket is similar with the second term of this bracket, means we can say first term of first bracket is cancelled with the second term of second bracket. So we can cancel it. Next, first term of second bracket we can cancel with second term of second bracket. First term of third bracket, it will be cancelled with the correct next bracket, and this process will continue up to the last bracket. Observe this last bracket. In last bracket, last term will cancel with the next one bracket first term. Result, only one term is remaining, and that is sin n minus 1 by 2 into d. See a1 sin d by 2 plus sin n minus 1 d, equation number 9. Observe this equation is similar with sin c plus sin d, and we know that this property sin c plus sin d is equal to sin c plus sin d is equal to sin c plus d by 2 into cos c minus d by 2, sorry 2, sin c plus sin d is equal to 2 sin c plus d by 2 into cos c minus d by 2. By using this property we can solve it. Now put this value, this whole value is equal to c, this value is equal to c, assume this value is equal to d. Put this value in this equation, then we can write 2 a1 sine of, from that calculation, nd by 2 into cos of n minus 1 by 2 into d. So this is the equation number 10. मुझे और कैलकुलेशन करना है, इसलिए मैं इसे वाइप करता हूँ. आपके पास ऑलरेडी रिकॉर्डेड है, तो ये आपको कभी भी आप देख सकते हो. इक्वेशन नंबर 10. See, in this equation sin d by 2 is there. Take sin d by 2 on this side from LHS to RHS. Then we can write 2 cos theta is equal to 2a, this a1 sin nd by 2 into cos n minus 1 n minus half d. 2 to get cancel in this equation. At the end one term is remaining r. 2 to get cancel. So r cos theta is equal to, finally r cos theta is equal to a1 sine of nd by 2 into cos of n minus half d. Equation number 11. This is the last derived equation from the along component. Similarly, इसी तरह हम जो परपेंडिकुलर नॉर्मल कंपोनेंट है उसके लिए भी इक्वेशन सॉल्व कर सकते हैं, डिराइव कर सकते हैं डिफरेंट वैल्यूज लेके, और हम ऐसा लिख सकते हैं r sin थीटा इज इक्वल टू a1 और a1 sin of nd by 2. There is on this side, sorry, one term is remaining, sin of d by 2. Similarly here one term is sin d by 2. okay. इसी तरह हम साइन के लिए भी लिख सकते हैं r sin of theta is equal to a1 sin nd by 2 upon sin d by 2 into sin of n minus half d. इक्वेशन नंबर 12. जिस तरह हमने इसे इक्वेशन को अगर हमने स्टार्टिंग में देखा होगा तो दोनों साइड में हमने 2 sin d by 2 से मल्टीप्लाई किया था. सिमिलरली हम नॉर्मल कंपोनेंट्स को भी 2 sin d by 2 से मल्टीप्लाई करेंगे दोनों साइड में और उसे सॉल्व करेंगे तो ये इक्वेशन हमें मिलेगा. r sin theta is equal to a1 sin nd by 2 upon sin d by 2 into sin n minus half d. Equation number 12. Now square on both side of equation 11 and equation 12. Then the new equation becomes r square cos square theta is equal to a1 square sin square nd by 2 upon sin square d by 2 into cos square n minus half d. Equation number 13. Similarly, from equation 12 we can write r square sin square theta is equal to a1 square into sin square nd by 2 upon sin square d by 2 into sin square n minus half d. Equation number 14. Equation 13 and equation 14. Now add equation 14 with equation 13. अगर हमने इसमें इसे ऐड किया तो क्या मिलता है, आर स्क्वेयर साइन स्क्वेयर थीटा प्लस आर स्क्वेयर कॉस स्क्वेयर थीटा. कॉमन कौन है, आर स्क्वेयर हमने आउटसाइड में लिया, ब्रैकेट में क्या रह गया, साइन स्क्वेयर थीटा प्लस कॉस स्क्वेयर थीटा. तो मैं ऐसा लिख सकता हूँ आर स्क्वेयर इनसाइड द ब्रैकेट साइन स्क्वेयर थीटा प्लस कॉस स्क्वेयर थीटा इज इक्वल टू, इसमें कॉमन कौन है, a1 स्क्वायर साइन स्क्वायर एन डी बाई टू अपॉन साइन स्क्वायर डी बाई टू, तो हमने वो बाहर ले लिया, तो ये a1 स्क्वायर साइन स्क्वायर एन डी बाई टू अपॉन साइन स्क्वायर डी बाई टू, ब्रैकेट में क्या रहेगा साइन स्क्वायर एन माइनस हाफ साइन स्क्वायर एन माइनस हाफ डी प्लस कॉस स्क्वायर एन माइनस हाफ डी। देखिए अकॉर्डिंग टू द ट्रिग्नोमेट्रिक प्रॉपर्टी दिस इज इक्वल टू 1, अकॉर्डिंग टू द ट्रिग्नोमेट्रिक प्रॉपर्टी दिस इज ऑल्सो इक्वल टू 1। अगर ये 1 हो गया ये 1 हो गया तो आपको क्या मिलेगा आर स्क्वायर इज इक्वल टू, ये सिंपल इक्वेशन हमने लिख दिया, a1 स्क्वायर इंटू साइन स्क्वायर एन डी बाई टू अपॉन साइन स्क्वायर डी बाई टू, क्योंकि ये 1 हो गया ये 1 हो गया, अब आर स्क्वायर रह गया। अब आर स्क्वायर का दोनों साइड से हमने स्क्वायर निकाल लिया, रिमूव द स्क्वायर ऑन बोथ साइड, सो आर इज इक्वल टू a1 साइन एन डी बाई टू अपॉन साइन डी बाई टू। ये मिला आपको इक्वेशन नंबर 15। इक्वेशन नंबर 16, observe the equation number 16. In this equation a is a very small, d is a very small, means we can write a tends to 0, d tends to also 0, and n is a very large, so n tends to infinity. इसमें ठीक से बोलते हैं कि a इज इक्वल टू 0, d इज इक्वल टू 0, n इज इक्वल टू इन्फिनिटी। अगर ऐसी केस है तो हम ऐसा बोल सकते हैं कि n इंटू a इज इक्वल टू n इज इक्वल टू a इज इक्वल टू फाइनाइट वैल्यू। सिमिलरली n इंटू d इज ऑल्सो इक्वल टू फाइनाइट वैल्यू। ये यहाँ पे थोड़ा समझ लीजिए, a is why tends to 0 because the value of a is infinitesimally small. अगर ये स्मॉल है तो 0 हो गया, d स्मॉल है तो 0 हो गया, लेकिन if n and a come together then they will be having the very large value, so it would high value, so that's why n into a is equal to finite value. Similarly d is the phase difference in between two successive rays which is also very small, so d is very small means n into d is equal to finite value. अब ये प्रॉपर्टी अगर हमने यहाँ पे यूज की तो हमें इक्वेशन 16 में पता चलता है, सॉरी 16 में ये पता चलता है कि d बहुत स्मॉल है, d बहुत स्मॉल है, तो इसलिए मैं ऐसा लिख सकता हूं r इज इक्वल टू a1 इंटू सिमिलरली साइंस एन डी by 2 upon, due to the value of d is very small tends to 0, so sin d by 2 tends to d by 2, so there is d by 2. We can also write this equation in this form, 2a1 into sin n d by 2 upon d. This is the equation number 17. See, in this equation nd by 2, nd is a very large value. Let us assume nd is equal to the particular value, finite value, and that value is equal to alpha. If n is a very large, d is a very small, then nd will be the very large and that value will be finite value. And let us assume here nd is equal to alpha, nd is equal to 2 alpha, not alpha, nd is equal to 2 alpha, and put this value in this equation, then this equation becomes r is equal to 2a1 sin 2 alpha upon 2 divided by d. From this equation d is equal to, मैं ऐसा लिख सकता हूं कि d is equal to 2 alpha by n. d is equal to 2 alpha by n. So put this value in this equation, equation number 17. So equation 2 alpha by n, this is equal to, ये n ऊपर जाएगा तो आपको मिलेगा 2a1 n into sin of 2 alpha upon 2 upon 2. So 2 to get cancel, 2 to this get cancel, so one term is remaining alpha, 2 to get cancel, so finally there is a1 into n sin alpha upon alpha, a1 into n into sin alpha upon alpha. लेकिन ये इक्वेशन बता रहा है कि n a1 इज इक्वल टू n a, तो मैं यहाँ पे पुट कर सकता हूँ n a1 इज इक्वल टू n a, और वो होगी फाइनाइट वैल्यू, और उसे हमने एज्यूम किया पर्टिकुलर वैल्यू विच इज a1. सो मैं यहाँ पे ये वैल्यू डाल के ये इक्वेशन ऐसे लिख सकता हूँ r इज इक्वल टू a1 साइन अल्फा अपॉन अल्फा, इक्वेशन नंबर 18, and this is the value of resultant amplitude for the single slit diffraction pattern. So resultant amplitude तो हमें मिल गई, अब हमें निकालना है value of intensity, and according to the relation of intensity we know that I is directly proportional to the R square, therefore I is equal to K R square. K is the constant of proportionality since K is equal to 1. So I is equal to R square from equation 18 हम लिख सकते हैं a1 square into sin square alpha upon alpha square. Again a1 means amplitude, that amplitude is not equal to resultant R. So मैं ऐसा कह सकता हूँ I is equal to a1 square is again value of intensity, let us assume that is I1 into sin square alpha upon alpha square. This is the value of resultant intensity in Fraunhofer single slit diffraction method. In next lecture we will study the condition for maxima, central maxima, minima and secondary maximas. Okay, good day, bye, thank you.